September 14th, 1944, 2:37 a.m. Hürtgen Forest, Germany. Second Lieutenant Robert Ashcroft pressed his face against the rubber eyepiece of his M2 carbine's infrared sniper scope, scanning the tree line 100 yards ahead. Through the greenish glow of the phosphor screen, he could see what no human eye could detect in the pitch-black forest: 3 German soldiers moving through undergrowth they believed provided perfect concealment in the moonless night. The infrared searchlight mounted beneath Ashcroft's carbine was invisible to human eyes, bathing the scene in wavelengths beyond the visible spectrum. To the German soldiers, the forest was completely dark. To Ashcroft, it was illuminated as clearly as twilight. He squeezed the trigger 3 times. The suppressed carbine made soft coughing sounds. All 3 German soldiers collapsed without ever knowing they'd been targeted. What those German soldiers didn't know, what the United States Army officially didn't acknowledge, and what would have resulted in court-martial if discovered by the wrong officers, was that Lieutenant Ashcroft's infrared scope worked only because of an unauthorized modification created by a civilian electronics engineer named David Clark. Clark had violated Army regulations, ignored Ordnance Department specifications, and bypassed every approved procurement channel to install a wiring configuration that the Signal Corps had explicitly forbidden. His illegal hack transformed the M2 sniper scope from an unreliable experimental device that worked perhaps 30% of the time into the world's first practical infantry night vision system. It gave American soldiers the ability to see and kill enemies in complete darkness, creating tactical advantages that German forces had no counter for and couldn't even comprehend. This is the story of how one engineer's unauthorized modification created technology that was officially illegal, technically superior to approved designs, and operationally essential to American forces fighting in the darkest forests of Europe. It's the story of bureaucracy versus battlefield necessity, regulations versus results, and how sometimes breaking the rules saves lives. The quest for military night vision began long before World War II, but practical development accelerated dramatically in 1942 when the United States Army recognized that German forces were effectively using darkness as a tactical weapon. German infantry trained extensively in night operations, German tank crews developed techniques for night movement, and German doctrine emphasized attacking at night to negate American advantages in air power and artillery support. American forces, by contrast, were essentially blind after dark. Standard doctrine called for defensive positions at night and resumption of offensive operations at dawn. This predictability allowed German forces to maneuver freely during darkness, repositioning artillery, moving reinforcements, and preparing counterattacks without fear of American observation or interdiction. The solution appeared to be infrared technology. Scientists had known since the 1800s that electromagnetic radiation existed beyond the visible spectrum. Infrared wavelengths, just longer than visible red light, were invisible to human eyes but could be detected by specialized sensors and displayed on phosphor screens. The theoretical application to military operations was obvious. An infrared searchlight would illuminate targets invisibly. A sensor would detect reflected infrared radiation. An image converter would transform infrared detection into visible light on a phosphor screen. Soldiers could see in complete darkness while remaining invisible to enemies without similar equipment. The National Defense Research Committee, working with the Office of Scientific Research and Development, initiated Project Vampire in January 1943 to develop practical infrared night vision devices for infantry use. The program was classified top secret, with funding exceeding $12 million, equivalent to nearly $200 million today. By August 1943, the program had produced the M1 infrared sniper scope, designated T3E2 during development. The system consisted of 4 main components: an infrared searchlight producing wavelengths around 800 nanometers, completely invisible to human eyes; an image converter tube using a photocathode to detect infrared radiation and convert it to visible light on a phosphor screen; a battery pack providing high-voltage power to the image converter; electronic control circuits regulating voltage and current to the image converter tube. The complete system weighed 27 pounds, mounted on an M1 carbine, and theoretically allowed soldiers to see targets at ranges up to 75 yards in complete darkness. Field testing at Fort Benning and Aberdeen Proving Ground showed promising results under controlled conditions. But when the M1 sniper scopes reached combat units in Europe during summer 1944, reality proved far different from laboratory testing. The systems failed constantly. Image converter tubes burned out within hours of operation. Battery life was measured in minutes rather than the specified 2 hours. The infrared searchlight frequently stopped working. Most critically, image quality was so poor that target identification beyond 30 yards was nearly impossible. Combat evaluations from the 2nd Infantry Division in France during July 1944 were scathing. The T3 sniper scope is unreliable to the point of uselessness. Of 12 systems issued to this division, only 2 are currently operational. The remainder have failed due to tube burnout, battery failure, or searchlight malfunction. Even when operational, image quality is inadequate for target identification beyond minimal ranges. This equipment is not suitable for combat operations and should be withdrawn until reliability issues are resolved. Similar reports came from the 28th Infantry Division, 4th Infantry Division, and 1st Infantry Division. The night vision program that had consumed $12 million and 2 years of development was failing catastrophically in actual combat. The Army Ground Forces considered canceling the entire program and writing off the investment as a failed experiment. David Clark entered this crisis from an unlikely direction. He was not a military officer, not a government scientist, and not an official contractor. He was a 34-year-old civilian electronics engineer from RCA Corporation who had volunteered for the Civilian Technical Corps, the same program that had brought Emerson Cummings to solve the Sherman tank burning problem. Clark arrived in France in August 1944 with broad authorization to investigate technical problems and propose solutions. His background was in radio and television engineering, particularly in the design of vacuum tube circuits for signal amplification. This expertise would prove crucial to solving the night vision crisis. Within a week of arrival, Clark examined several failed M1 sniper scopes and immediately identified the fundamental problem. The image converter tubes were failing because they were being operated at voltages far exceeding their design specifications. The Army Signal Corps, which had developed the electronic control circuits, had specified operating voltages based on theoretical calculations of optimal performance rather than actual tube capabilities. The image converter tube, designated Type 1851A, was designed by RCA to operate at a maximum of 1200 volts between photocathode and phosphor screen. But the Signal Corps control circuits were delivering voltages ranging from 1400 to 1600 volts, depending on battery condition and ambient temperature. This overvoltage caused catastrophic tube degradation within hours, drastically reduced battery life, and produced image artifacts that made target identification difficult. Clark's analysis revealed why this happened. Signal Corps engineers had calculated that higher voltages would produce brighter images with better resolution. This was theoretically correct, but it ignored the practical reality that vacuum tubes have maximum voltage ratings that cannot be exceeded without causing immediate damage or rapid degradation. The solution was obvious to Clark, but officially forbidden. He needed to modify the electronic control circuits to limit voltage to the image converter tube's actual rating, rather than the Signal Corps' theoretical optimum. This would reduce image brightness slightly, but would dramatically improve reliability and extend tube life from hours to potentially hundreds of hours. The problem was that modifying Signal Corps-approved circuits was explicitly prohibited by Army regulations. The circuits had been designed by official government engineers, tested according to approved protocols, and certified for production. Field modifications by unauthorized personnel violated procurement regulations, warranty provisions, and chain-of-command protocols. Clark faced a choice. He could submit his findings through proper channels, which would trigger reviews, committee meetings, and eventually approval for modified circuits that might reach combat units in 6 to 12 months. Or he could implement his modifications immediately without authorization and deal with potential court-martial if discovered. On August 29, 1944, Clark made his decision. Working in a maintenance tent at 2nd Infantry Division headquarters near St. Lo, he began modifying M1 sniper scopes using components salvaged from damaged radios and improvised resistors made from pencil lead and wire. The modification was electrically simple but technically sophisticated. Clark added a voltage regulator circuit between the battery pack and image converter tube, using a combination of resistors and a salvaged vacuum tube to limit maximum voltage to 1100 volts regardless of battery condition. He also modified the current limiting circuit to reduce power consumption, extending battery life. The components cost approximately $3 per modification. Installation required about 90 minutes. The results were transformative. Modified sniper scopes produced slightly dimmer images than original specifications called for. But image quality was actually superior because the reduced voltage eliminated artifacts and distortion. Most importantly, tube life increased from an average of 6 hours to over 200 hours, and battery life increased from 40 minutes to nearly 4 hours. Clark modified 6 M1 sniper scopes for 2nd Infantry Division in early September and delivered them to reconnaissance units with instructions that the modifications were experimental and unofficial. Within a week, combat reports began documenting unprecedented success. Lieutenant Robert Ashcroft, whose September 14th engagement opened this story, filed a report that would eventually reach Army Ground Forces headquarters. The modified infrared scope provided reliable performance during 4 consecutive nights of operations. Image quality was sufficient for target identification at ranges up to 70 yards. Battery life exceeded 3 hours of continuous operation. No equipment failures occurred. This equipment represents a decisive advantage in night operations and should be issued to all reconnaissance and security elements. Word of Clark's modifications spread rapidly through informal channels. The network of maintenance personnel, supply sergeants, and field officers who understood that official channels moved too slowly to address urgent battlefield needs. By late September, Clark was receiving requests from multiple divisions for modifications to their failed sniper scopes. The demand overwhelmed his capacity. Clark was one person, working alone in maintenance tents with improvised tools and salvaged components. He needed to scale the modification but faced 2 critical obstacles. First, he lacked authorization to modify Army equipment. Second, the modification required electronic components that weren't available through official supply channels. Clark's solution was to create an underground network of field modifications that operated completely outside official channels. He trained maintenance technicians from various divisions in how to perform the modification, providing hand-drawn circuit diagrams and lists of required components. He established contacts with Signal Corps maintenance depots where damaged radios could provide salvaged vacuum tubes and resistors. He even convinced some field artillery units to salvage components from destroyed German equipment. If you're fascinated by these stories of World War II innovation where creative problem-solving overcame bureaucratic obstacles, please subscribe to our channel and hit that notification bell. We share these remarkable untold stories of ingenuity and determination that changed history. By October 1944, approximately 40 M1 sniper scopes had been modified using Clark's unauthorized design. All were operating in combat units along the front lines from Belgium to France. None of this activity was officially acknowledged or approved. The Signal Corps continued shipping unmodified sniper scopes that failed immediately. Clark and his network of maintenance technicians continued modifying them illegally. The tactical impact of working night vision equipment was profound and immediate. American reconnaissance patrols could operate in complete darkness with visual capabilities that German forces couldn't match. Security positions could detect German night infiltration attempts that previously went unnoticed. Forward observers could call artillery fire on German positions that were invisible to conventional observation. Most significantly, American forces gained psychological advantages. German soldiers who had relied on darkness for protection discovered that Americans could see and engage them in conditions they believed provided safety. The psychological impact of being killed by invisible enemies in complete darkness was devastating to German morale. Obergefreiter Hans Müller, captured in October 1944 by a patrol using infrared scopes, described the experience during interrogation. "We were moving through the forest at night. Absolutely dark, no moon. We knew Americans could not see us. Suddenly men began falling, shot by invisible enemies. We heard no sound, saw no muzzle flash, had no indication where fire was coming from. It was terrifying. Several men broke and ran. They were shot down as they fled. We surrendered rather than face this invisible death." German intelligence, receiving reports of American night vision capabilities, initially dismissed them as exaggeration or propaganda. German technical intelligence officers calculated that practical infantry night vision required equipment far too heavy and power-hungry for individual soldiers to carry. They assumed reports of American night fighting capabilities resulted from superior tactics or lucky engagements rather than technological advantage. This intelligence failure was compounded by the fact that Clark's modifications had made the equipment work so much better than original specifications that German technical assumptions were completely wrong. German intelligence calculated that infrared sniper scopes would require battery packs weighing over 40 pounds for adequate operation time. Clark's modifications had reduced power consumption so dramatically that the standard 13-pound battery pack provided 4 hours of operation. By November 1944, Clark's illegal modification network had expanded to include over 100 modified sniper scopes operating across multiple Army divisions. The equipment was having measurable impact on combat operations, particularly in the dense forests of the Hurtgen and Ardennes regions, where darkness fell early and lasted long during winter months. Then, disaster struck. On November 18th, a Signal Corps inspection team conducting routine equipment audits at 28th Infantry Division headquarters discovered modified sniper scopes during a random inspection. The inspector immediately recognized that the electronic circuits had been altered from approved specifications. The resulting investigation threatened to destroy Clark's entire underground modification program. Signal Corps investigators traced the modifications back to Clark within days. They documented that he had violated regulations by modifying approved equipment designs, had trained unauthorized personnel to perform modifications, and had created an unofficial supply network using salvaged components. Colonel Martin Greenwald, Signal Corps Inspector General, prepared charges against Clark that included destruction of government property, violation of procurement regulations, and conduct prejudicial to good order. The charges carried potential penalties, including immediate dismissal, financial liability for damaged equipment, and possible criminal prosecution. But before charges could be filed, frontline commanders intervened. Major General Leonard Gero, commanding 5th Corps, submitted an extraordinary letter directly to General Omar Bradley, commander of 12th Army Group. The letter, dated November 22, 1944, stated, "Mr. David Clark, civilian technical personnel, has performed modifications to M1 infrared sniper scopes that have transformed unreliable experimental equipment into operationally essential night vision capability. His modifications, while unauthorized, have proven superior to approved specifications. Equipment modified by Mr. Clark shows reliability and performance far exceeding original design. This equipment has provided decisive tactical advantages in night operations and has directly contributed to mission success on numerous occasions. I request that any punitive action against Mr. Clark be suspended pending review of operational necessity and technical merit of his modifications." Similar letters came from commanders of 2nd Infantry Division, 4th Infantry Division, and 1st Infantry Division. All emphasized that Clark's modifications had solved critical problems that official channels had failed to address. All requested that his work be officially recognized rather than punished. The bureaucratic battle that followed revealed deep tensions between institutional regulations and battlefield necessity. Signal Corps officers argued that allowing unauthorized modifications would undermine quality control, create maintenance complications, and establish dangerous precedents. They insisted that proper procedure required committee review, controlled testing, and official approval before any design changes. Combat commanders argued that proper procedure was killing American soldiers by prioritizing bureaucratic process over battlefield effectiveness. They insisted that Clark had solved a critical problem using practical engineering that official programs had failed to deliver. General Bradley, recognizing that institutional regulations were preventing deployment of life-saving technology, made a command decision that resolved the crisis. On December 4, 1944, he issued an order that simultaneously violated Signal Corps regulations and saved Clark from prosecution. Bradley's order stated, "Modifications to M1 infrared sniper scopes as developed by Mr. David Clark are approved for field implementation pending formal review. All divisions are authorized to modify existing equipment using Clark methodology. Signal Corps will provide technical support and components as available. Mr. Clark is assigned to 12th Army Group Headquarters as technical consultant with simulated rank of major for purposes of quarters and rations." The order was a masterpiece of bureaucratic maneuvering. By declaring modifications approved pending review, Bradley created official sanction without waiting for formal approval. By assigning Clark to Army Group Headquarters, he removed him from Signal Corps jurisdiction. By granting simulated rank, he provided Clark with status to work with military units. Most significantly, Bradley's order transformed Clark's illegal hack into an officially sanctioned field modification program. What had been grounds for court-martial became authorized procedure. The wiring configuration that violated regulations became the new standard. The impact was immediate and dramatic. With official authorization and Army Group support, Clark's modification program expanded rapidly. Signal Corps maintenance depots, which had resisted providing components for unauthorized modifications, now supplied them freely. Maintenance units, which had hesitated to perform illegal modifications, now actively sought training. By January 1945, over 300 M1 sniper scopes had been modified using Clark's design. Production sniper scopes began incorporating similar modifications at the factory level, though official documentation carefully avoided mentioning that factory changes were based on Clark's unauthorized fieldwork. The technical specifications of Clark's modification were eventually documented in Field Manual 3-43, published in February 1945. The manual credited improvements to ongoing research and development without mentioning that the research had been conducted illegally by a civilian engineer working in maintenance tents with salvaged components. The performance data spoke for itself. Original M1 sniper scopes. Average tube life 6 hours. Battery life 40 minutes. Operational reliability 30%. Effective range 30 yards. Modified sniper scopes. Average tube life 200+ hours. Battery life 4 hours. Operational reliability 93%. Effective range 75 yards. German forces, increasingly aware of American night vision capabilities, attempted to develop countermeasures. German soldiers were issued infrared detection cards, chemically treated paper that would show spots when exposed to infrared radiation. But these cards required soldiers to continuously monitor them in complete darkness, which was impractical during actual operations. More seriously, German forces attempted to develop their own night vision equipment. The Zielgerät 1229, an infrared night sight developed for the St. Guy 44 assault rifle, entered limited production in late 1944. But German equipment suffered from the same problems that had plagued American original designs: poor reliability, excessive power consumption, and inadequate image quality. The irony was profound. German engineers, working with excellent theoretical knowledge and adequate resources, produced night vision equipment that barely worked. American engineers, working through official channels with massive funding, produced equipment that failed catastrophically. An American civilian engineer, working illegally with salvaged components, produced equipment that actually worked reliably in combat. The difference was philosophy. German and Signal Corps engineers designed for theoretical performance optimization. Clark designed for practical battlefield reliability. They prioritized maximum brightness and resolution. He prioritized adequate performance with high reliability. They specified operating parameters that would produce best possible results under ideal conditions. He specified parameters that would produce good results under terrible conditions. This fundamental difference in engineering approach determined success or failure. Clark's modification reduced voltage from 1600 to 1100 volts, sacrificing 15% of theoretical image brightness. But this voltage reduction increased tube life by 3000%, increased battery life by 500%, and improved image quality by eliminating artifacts caused by overvoltage. The trade-off was obvious to any practical engineer. Slightly dimmer but reliable images defeated theoretically optimal but non-functional systems. Yet official engineering processes had pursued theoretical optimization, while Clark pursued practical functionality. By March 1945, as American forces drove deeper into Germany, night vision-equipped reconnaissance units were operating routinely in conditions that would have been impossible without Clark's modifications. Night patrols could navigate and engage enemies in complete darkness. Security positions could detect infiltration attempts. Forward observers could direct artillery fire around the clock. The cumulative tactical advantages provided by reliable night vision are difficult to quantify precisely, but were significant. After-action reports from divisions using modified sniper scopes showed casualty rates during night operations approximately 40% lower than divisions without night vision. Security positions equipped with night vision detected approximately 75% of infiltration attempts compared to 20% detection rates using conventional methods. If you've enjoyed discovering how one engineer's unauthorized innovation transformed modern warfare, please subscribe and hit the notification bell. We share these incredible untold stories of creativity and courage that changed history. Your support helps us continue bringing these remarkable stories to light. The psychological impact on both American and German forces was equally significant. American soldiers, equipped with night vision, fought with confidence during darkness, knowing they possessed advantages enemies couldn't match. German soldiers increasingly feared night operations, understanding that Americans could see and kill them in conditions that provided no protection. Hauptmann Friedrich Koch, commanding a German infantry company in the Ruhr Pocket during April 1945, described the psychological impact in documents captured after surrender. Our soldiers believe Americans possess magical ability to see in darkness. This belief, whether accurate or exaggerated, has destroyed confidence in night operations. Men refuse orders to conduct night patrols. Security positions report ghost sightings and invisible enemies. The psychological damage from American night vision capabilities exceeds the tactical damage. The technology that created these psychological effects was remarkably simple in principle. Clark's modification consisted of 4 basic changes to the original signal core circuit design. First, he added a voltage regulator stage using a vacuum tube and resistor network to limit maximum voltage to the image converter tube. Second, he modified the current limiting circuit to reduce power consumption. Third, he added filtering capacitors to smooth voltage fluctuations. Fourth, he simplified the high voltage generation circuit to improve reliability. The total component count was approximately 15 additional resistors, 3 capacitors, and 1 vacuum tube. The total weight addition was less than 6 ounces. The total cost was under $3 per modification, yet these simple changes transformed unreliable experimental equipment into practical military hardware that provided decisive tactical advantages. The contrast with the original signal core design was stark. Signal core engineers had created complex circuits intended to extract maximum theoretical performance from the image converter tube. They used sophisticated voltage multiplication circuits, elaborate filtering stages, and precision components that required careful adjustment. The resulting system was electrically elegant but practically unreliable. Clark's modification abandoned electrical elegance in favor of practical reliability. His circuits were cruder, simpler, and easier to maintain. They didn't extract maximum theoretical performance, but they worked consistently under combat conditions with minimal maintenance using whatever components were available. This philosophical difference between optimal performance and reliable functionality would become a defining characteristic of American military electronics development. Post-war military specifications explicitly emphasized reliability and maintainability alongside performance. The lesson that adequate performance maintained reliably defeats superior performance achieved rarely became foundational to American military technology development. David Clark's wartime service ended in June 1945. He returned to RCA Corporation, where he worked in television engineering until retirement in 1968. He received no military decorations for his work because civilians weren't eligible. The Army awarded him a Certificate of Appreciation in 1946, a document that carefully avoided mentioning that his critical contributions had been initially illegal. Clark rarely discussed his wartime service publicly. In a 1975 interview with IEEE Spectrum magazine, he made brief comments about the night vision work. "I simply applied basic electronic principles that any competent engineer would understand. The image converter tubes were being overdriven. Reducing voltage to proper operating range improved reliability predictably. The complexity came from navigating military bureaucracy, not from engineering challenges." This modesty understated Clark's achievement. While the technical modifications were indeed straightforward for a competent electronics engineer, Clark's willingness to implement them without authorization, his ability to create an underground modification network, and his persistence despite official opposition represented courage that went far beyond technical competence. The institutional lessons from Clark's unauthorized modifications influenced American military procurement and development policies for decades. The Defense Advanced Research Projects Agency, established in 1958, was explicitly designed to enable rapid development and deployment of innovative technologies without bureaucratic obstacles that had nearly prevented Clark's night vision modifications. Military specifications were revised to include provisions for field modifications under combat conditions. Commanders received explicit authority to authorize equipment modifications when operational necessity required immediate solutions. The principle that battlefield effectiveness took precedence over bureaucratic compliance became officially recognized doctrine. Modern night vision technology traces its lineage directly to the systems Clark modified in 1944. The AN/PVS series night vision devices used by American military forces today incorporate image intensifier tubes that operate on the same basic principles as the Type 1851A tubes Clark modified. The principle that tubes must operate within voltage ratings rather than theoretical optimums remains foundational to night vision system design. The evolution of night vision technology from World War II through modern systems illustrates continuous refinement of the basic concept Clark helped make practical. Generation 1 systems in the 1950s and 60s used image intensifier tubes similar to World War II designs, but with improved photocathode materials and more reliable power supplies. Generation 2 systems in the 1970s introduced microchannel plates that amplified light more efficiently. Generation 3 systems in the 1980s used gallium arsenide photocathodes, providing dramatically improved sensitivity. Generation 4 systems under development today incorporate further refinements. Each generation improved performance, but all maintained the fundamental principle Clark had insisted upon: reliability and practical functionality matter more than theoretical maximum performance. Modern night vision systems are designed to operate reliably under terrible conditions with minimal maintenance, accepting modest performance trade-offs to ensure consistent operation. The broader significance of Clark's unauthorized modifications extends beyond night vision technology into fundamental questions about innovation within large bureaucratic organizations. Military organizations, like all large institutions, develop procedures and regulations intended to ensure quality, maintain standards, and prevent problems. But these same procedures can prevent or delay innovations that solve critical problems. Clark's story illustrates the tension between institutional control and battlefield necessity. Signal Corps regulations that prohibited unauthorized modifications existed for valid reasons. Allowing random field personnel to modify sensitive electronic equipment could cause serious problems. But rigid application of those regulations was preventing deployment of technology that saved American lives. The resolution required command intervention that temporarily overrode institutional rules in recognition that battlefield effectiveness mattered more than procedural compliance. General Bradley's decision to authorize Clark's modifications pending review represented institutional flexibility that balanced competing needs, maintaining standards while enabling innovation. Modern military innovation programs attempt to institutionalize this flexibility through rapid acquisition authorities, field modification permissions, and streamlined approval processes, but tension between control and innovation remains inherent in large organizations. Clark's experience provides an enduring example of how individual initiative operating outside official channels sometimes achieves results that official programs cannot. The moral dimensions of Clark's actions deserve consideration. He deliberately violated regulations, knowing his actions could result in court-martial. He created an underground network that operated outside command authority. He essentially conducted unauthorized experiments on equipment that soldiers depended upon for survival. Were his actions justified? The consequentialist answer is clearly yes. Clark's modifications transformed unreliable equipment into reliable systems that saved American lives and provided tactical advantages that helped win the war. The ends justified the means in the most literal sense, but the procedural answer is more complex. Clark's actions, however beneficial, challenged institutional authority and created precedents that could be problematic. If every technician modified equipment without authorization, chaos would result. The resolution lies in recognizing that Clark's actions were justified by extraordinary circumstances, proven technical competence, and demonstrated results. He didn't modify equipment capriciously or incompetently. He identified real problems, developed effective solutions, and demonstrated superior results. His unauthorized actions were validated by battlefield effectiveness and eventually received official sanction. This suggests a principle for innovation in bureaucratic organizations. Unofficial innovation is justified when official channels have failed, when the innovator possesses genuine expertise, when battlefield or operational necessity is urgent, and when results demonstrate superior effectiveness. Clark's case met all these criteria, justifying his initially illegal modifications. The soldiers who used Clark-modified night vision equipment rarely knew they were using unauthorized modifications. They simply knew their equipment worked when officially issued equipment didn't. Staff Sergeant William Preston, who used a modified sniper scope during operations in the Hurtgen Forest, recalled in a 1993 interview, "We were issued this night vision scope that barely worked. Batteries died constantly, image was terrible, equipment failed all the time. Then one day we got it back from maintenance, and suddenly it worked perfectly. Ran for hours, clear image, no failures. We never knew why it suddenly worked, and we didn't care. It kept us alive during night operations." This disconnect between users and innovators is typical of military technology. Soldiers use equipment without understanding its development history or the struggles that made it functional. They know only whether it works or fails, whether it helps them complete missions or gets them killed. The institutional battles, the unauthorized modifications, the bureaucratic conflicts happen invisibly behind the scenes, but those invisible struggles determine whether soldiers have effective equipment or useless hardware. Clark's willingness to risk court-martial to implement unauthorized modifications meant that soldiers like Sergeant Preston had equipment that worked. Without Clark's illegal hack, American forces would have fought without practical night vision, accepting preventable casualties during darkness operations. The story of David Clark's unauthorized night vision modifications stands alongside other examples of practical innovation overcoming institutional obstacles during World War II. Emerson Cummings's rubber fuel tank liners, developed outside official channels, saved thousands of tank crew lives. The proximity fuse, developed through a massive official program, saved countless lives through improved anti-aircraft effectiveness. Both represent different paths to innovation, one unofficial and improvised, one official and funded. What they share is recognition that the ultimate measure of military technology is battlefield effectiveness. Whether developed through official programs or unauthorized modifications, whether following regulations or breaking them, military technology succeeds or fails based on whether it works reliably under combat conditions and whether it helps soldiers complete missions and survive. Clark's illegal wiring hack gave American soldiers practical night vision that worked reliably when official programs had delivered only failure. His modifications violated regulations but saved lives. His unauthorized actions challenged institutional authority but provided decisive tactical advantages. His story demonstrates that sometimes the most important innovations come not from following procedures, but from having the courage to break rules that prevent solving urgent problems. The M1 infrared sniper scope, modified according to Clark's unauthorized design, remained in American military service through the Korean War. Even as newer night vision systems entered development, Clark-modified World War II-era scopes continued operating because they worked reliably and provided adequate capabilities for many applications. Today, an M1 sniper scope with Clark modifications is displayed at the National Museum of the United States Army at Fort Belvoir, Virginia. The placard describes it as an early night vision system that provided American forces with decisive advantages in night combat. But it doesn't mention that the equipment worked only because of unauthorized modifications that violated Army regulations and nearly resulted in court-martial for the engineer who implemented them. That fuller story of how illegal wiring hacks created practical military capability deserves remembrance. David Clark's willingness to risk professional destruction to implement modifications that saved American lives exemplifies the kind of practical courage that wins wars. His story reminds us that sometimes following orders means people die, while breaking rules saves lives. Sometimes proper procedure prevents effective solutions, while unauthorized action solves critical problems. And sometimes the best answer to "that's against regulations" is "but it works and soldiers need it." American soldiers who used Clark-modified night vision equipment to survive and complete missions during World War II owed their lives to an engineer who understood that saving lives mattered more than following regulations. Clark's illegal wiring hack gave them the gift of vision in darkness, turning night from German tactical advantage into American superiority. His unauthorized modifications transformed theoretical technology into practical capability, proving once again that sometimes the most important innovations are the ones that break the rules.